Now, something we've been hinting at the entire time is that if torque is analogous to force, well then the sum of the force, which is equal to mass times the linear acceleration, is going to have a rotational component too. In this case, the sum of the torques is equal to moment of inertia times angular acceleration. Again, you want to think of everything in linear quantities translated over to rotational quantities. So again, we said that force is going to be very similar to torque. Moment of inertia, again, inertia is a measure of its mass, is how we rewrite mass, and angular acceleration is the translated version of linear acceleration. So this situation will only be used if an object is not in equilibrium, meaning that the forces applied will cause acceleration, angular acceleration to be more specific. So since this example is entirely something you've never seen before, you're going to need to include it for full credit in your notes. Consider a beam of length L, mass m, and a moment of inertia about the center of mass 1/12 ml squared. It is pinned to a hinge on one end. Determine the beam's angular acceleration. So just like in forces, we're going to start off with a free body diagram and label all of the forces acting on this beam. If it's a beam of length L, mass m, that means our center of mass will be located right in the middle. And on this center of mass is where gravity will act. Now we do have a couple of other forces acting on this beam, coming from the hinge. So the hinge is providing vertical forces and horizontal forces at all times. But because these forces are located a distance of 0 away from the rod, they don't actually provide any torques. So this mg is the only thing that's providing torque or causing rotation. So the first thing we want to do is find out the component of mg that is perpendicular to r. So if we look at this problem like an incline, we can see that mg can be broken down into components. And this component that's going to be perpendicular to the lever arm is going to be mg cosine theta. Now this theta right here is the same theta given to us in the problem, so that's convenient. Now this r, the distance away from my axis of rotation, is going to be equal to L divided by 2, the length of the rod divided by 2. So the sum of our torques is equal to the moment of inertia times the angular acceleration. So RF sine theta is equal to I alpha, and R is L divided by 2, F is mg cosine theta, and the angle between L divided by 2 and mg cosine theta is 90 degrees. They're already perpendicular, so this piece becomes unnecessary, equal to I alpha. Now again, what we're trying to do is solve for your angular acceleration. But the problem is, before we do that, is this moment of inertia. Now we know that a moment of inertia is mr squared, where r is a distance away from your axis of rotation. But the problem is that the moment of inertia that we're given is about the center of mass. But we're not rotating about the center of mass. We're rotating about one end. So what we can do is actually use the parallel axis theorem, which is the moment of inertia about the center of mass plus the mass, total mass, times the distance that the axis of rotation has moved from the center of mass. In this case, we're given 1/12 ml squared as our moment of inertia about the center of mass. The total mass is m, and the distance that the axis of rotation has been moved is L divided by 2. L divided by 2 mg cosine theta is equal to 1/12 ml squared plus ml divided by 2 squared times alpha. Now if we simplify this right-hand side, we get 1/12 ml squared plus ml squared over 4. Finding a common denominator, we get 4/12 ml squared, or 1/3 ml squared. That simplifies down to, and again, here we're trying to solve for our angular acceleration. One of our L's is going to cancel out, the masses will cancel out, and we're left with 3/2 g L cosine theta is equal to our angular acceleration.